Okay, so we're here. It's September the 9th, and we're here to talk about compound nomenclature for our introductory chemistry class. And we'll pick up where we left off. We had an introduction to representative ionic nomenclature, compound nomenclature with representative metal cations. Okay, so I will, to review, I'll do one or two of those and then we'll continue on. Okay, so again, if we have something, say, so how do we name this? Very simple. Name of cation, name of anion. Name of cation is magnesium, same name as the parent neutral element, and the anion is phosphide. We don't care how many of them there are. All right, we don't care that there's 3 magnesiums and 2 phosphides. Okay, so name of cation, name of anion. Now, let's look at the reverse. What if we're given the name? How do we come up with the formula unit here? Remember, the formula unit is what we call the chemical formula for an ionic compound, the lowest whole number ratio between the cations and anions in an ionic compound. All right, so how do we do this? Well, we can write here the charge on magnesium cation is 2+, charge on phosphide is -3. So we'll write the symbols down here, okay? And we're gonna take these charges and flip them and make them the subscripts. In other words, how many magnesium cations and how many phosphide anions. So the charges become the how manys, all right? The how many. They're gonna tell us how many of each ion type we have in the compound. Okay, any questions there? Any questions?
How did you get positive on magnesium?
From the periodic table, it's an alkaline earth, right? So it's a metal. First off, we ask, is it a metal or non-metal? It's a metal, so we know the charge is positive. And we put our finger on magnesium and count to the nearest inert gas. So we go backwards 1 to sodium and then backwards 1 to neon. So it's 2 away from the nearest inert gas, right? 2 away. The same with phosphide. I ask, is it a metal or a non-metal? It's a non-metal, so the charge is negative. Negative how many? Well, I put my finger on phosphorus and I count to the nearest inert gas. So phosphorus is 0, sulfur is 1, chlorine is 2, and argon is 3. And that's where the 3 comes from, right? You're just counting to the nearest inert gas. Okay, any other question or comments? Did that clear up, whoever asked that?
Yes.
Okay, so any questions or comments? All right, we'll do one more here and then we'll continue on with the water subhydration here.
And what are these called again? Just so I can put a label. And what are these compounds called again? So I can put a label.
Ionic compounds.
Okay.
Because they contain ions. They contain ions, ionic. All right, so let's look at another formula unit here. Again, pay attention to this one. Okay, so we want a name here. Well, there's calcium. And remember, by convention, we always put the cation first. Now, I cover up that metal. What's left is my anion. I see 2 capital letters there. That tells me there's more than one element. There's more than one element. So I'm going to be looking on my polyatomic ion list that we gave you last class. My polyatomic ion list. And I see that SO4 is sulfate. Sulfate. Right? Calcium sulfate. Name of cation, name of anion. Again, you cover up the metal. All right, by convention, the metal cation is always first, and what's left is your anion, regardless of how many atoms there or elements are there. That's your anion. Now, again, how about the reverse? What if we're given the name and we have to come up with the formula unit? Well, I look on my periodic table. Calcium has a charge of +2. Right, it's a metal, so it's positive, and it's 2 away from argon. And I look at the polyatomic ion list, and I see the charge on sulfate is -2. -2. So I can write Ca for calcium, SO4 for sulfate. Then I can take this 2 and put it here. I'm going to write it in a different color here. All right, so 2 calciums, and then we're going to have 2 sulfates. But this is polyatomic ion. If I write a 2 there, that looks like 42 oxygens. So we need parentheses. We need parentheses. So 2 calciums and 2 sulfates. All right, remember that a subscript multiplies what comes before it. So what comes before that 2? A parenthesis. So whatever's inside the parenthesis gets multiplied by 2. Are we done here with this calcium sulfate formula unit?
No.
No? What's wrong?
Play.
Need simplify?
I speak louder. I can barely hear you.
You need to simplify it?
Yes, there's a common factor. Okay, I turned up my speakers. There's a common factor of 2. If we have a common factor, we must divide out by that common factor. So 2 divided by 2 is 1, 2 divided by 2 is 1. So when we do that, we end up with CaSO4, which is what we started out with up here. Right? You always have to check and make sure there's not a common factor. Right? You always have to check and make sure. Okay? Any question or comment on that one? I'm gonna do one. Actually, we'll move on with the waters. Do we have any question or comment on this one? Any question or comment? All right, we'll move on. Okay. So now, let's look at this one. Let's see. Well, we're going to run out of room here. Start over here. So we need to come up with a formula unit for this. All right? Now, we'll talk about this trihydrate in a moment. Let's just deal with this the same way we've been dealing with it. Okay? Well, I look on the periodic table. Sodium has a charge of +1. All right, phosphite, it does not end in IDE, so I know it's a polyatomic ion. All the monoatomic representative anions all end in IDE. Fluoride, chloride, oxide, sulfide. All right, so I look on the polyatomic ion list and I see that phosphite's charge is -3. -3. So all we got to do is write the element or the ion symbols and then flip the charges. So I can come down here and I can write sodium is Na. All right, phosphite is PO3. And now I'm going to take these charges in red and flip them. And they're going to become the how many for the ions down below. So the 3 will come with the sodium. The 1 will go with the phosphite. I don't need to write it. So there's sodium phosphite. But that's not our compound. Our compound is sodium phosphite trihydrate. All right, and now this prefix 3 that we copied down a moment ago, okay, the prefix 3 sides in a the prefix tri means 3. There's 3 sides in a triangle, right? So what we're going to do here is we're going to put a bullet and then 3, and hydrate means water. Hydrate means water. So 3 water molecules. 3 water molecules. So there's the formula unit for this compound. 3 sodiums, 1 phosphite, bullet, and 3 waters. What are called waters of hydration. Waters of hydration. Let's talk about these for a moment since we're seeing these for the first time. Waters of hydration. Okay, and it's kind of a shame because we usually do a pretty neat lab with these waters of hydration. We figure out how many, we figure out what this number is here. Okay, given a sample of the compound. Do an experiment, you can figure out what that number is. So what are these waters of hydration? Now, because we're not at school, I have a nice model of an ionic compound, and I can show it to you. These ionic compounds are crystalline, which means they're like three-dimensional wallpaper. They have a repeating pattern in 3 dimensions. That's what a crystal is. It's a repeating pattern in 3 dimensions, a crystalline solid. Okay, now sometimes when these compounds form, a lot of them are formed, some chemical reaction occurs in water, and the solid compound will precipitate out. Okay, and sometimes it will drag along some water molecules as part of that crystal structure. As part of that crystal structure, it will drag. Okay, so so in this particular compound, the waters are just as important as the sodiums, just as important as the phosphite. Right, they are just as much a part of the compound. I should mention that this sodium phosphite trihydrate and Na3PO3, well, they look like similar compounds, but they can be dramatically different. They will have different melting points, maybe different indices of refraction. In some cases, they can even be different colors. All right, although that's usually when you have a transition metal cation as a transition metal as the cation. Then you can see different colors. With representative, they'll usually be the same color. Okay, but again, they are an intricate part of the 3-dimensional crystalline pattern, repeating pattern. Okay, so this will have one particular crystal structure. This will have another, could be totally different crystal structure, because now you have these these water molecules as part of the 3-dimensional wallpaper. That's repeating. Okay, now we gave you the prefixes 1 through 10. All right, so you specify the number of waters with one of these prefixes. All right, mono for 1, di for 2, okay, etc., all the way up to nona for 9 and deca for 10. All right, there are ones beyond further than that, but we'll just go with the ones 1 through 10. Okay, so do we understand what these waters of hydration are? Sometimes just by heating up the compound, that's the experiment you would have done. You just can heat up the compound and drive these waters away. They will evaporate away. So you can turn this compound into this compound. Okay, you can't always do that. Sometimes this one will just decompose, right? But sometimes you can just heat it up and these will evaporate away. They are just water molecules after all. Okay, any question on this? All right, now, what if we're given the formula unit here and we have to come back to the name? Well, let's have a look at this. Name of cation, name of anion. Sodium is the cation. I don't care that there's 3 of them. And phosphite is the anion. And remember, you're covering up the sodium here. And I see 2 elements left. So I know it's on the polyatomic ion list. So sodium phosphite. Sodium phosphite. All right, so that takes care of this in black. Now we need the waters. Well, 3 is tri, and water is hydrate. Just what we started with up at the top. Just what we started with up at the top. So again, as you saw from your assignment from last class a week ago, you have to be able to go both ways. I give you the name, you give me the formula unit. I give you the formula unit, you give me the name. Okay? Any question there? Any questions? All right.
Actually, I've got one for you.
Sorry?
No, I've got one for you. For the hydrate, would it at the end of it, or is it always going to be ATE on the end?
It's always going to be ATE.
Okay.
Always. It's going to be some prefix, one of those 10 prefixes, and then hydrate. So the hydrate means water.
Okay.
Right? And
Perfect.
the prefix is going to tell us how many water.
All right. Thank you.
No problem. You got a question, ask. Hardly anybody ever ask any questions. All right. I never know if people understand if people don't ask any questions. All right. Let's look at another one here. Let's do one where I give you the formula first. Actually, this is one that we would, oh, that's a transition metal. We don't want to do that one. Now, I'm just making these up off the top of my head. I don't know if this hydrated compound is a real compound. It's probably not. Okay, now, let's take a look here. Name of cation. So Be is beryllium. Be is beryllium. Actually, this green I don't think shows up too good on the video. So I'm going to try to avoid using it. All right, so beryllium. Now, I cover up the metal. What's left is my anion. All right, I see there's two of them. I know it's a polyatomic ion because it's got parentheses. But furthermore, it's got two capital letters, C and O. So I know that's a polyatomic ion. I'm going to look on the polyatomic ion list, and I see that ClO4 is perchlorate. Perchlorate. All right. And then we have 6 waters. And we should know that 6 is hexa. Hexa. Right? Hexahydrate. Hexahydrate. Okay? Simple enough. Just name of cation, name of anion, and then how many waters. Right? How many waters. All right? Any question there? All right, let's go the reverse way, the flip way, where we're given the name and we want to reproduce this formula unit up here. All right, so I look on the periodic table. Charge on beryllium is +2. It's a metal, so it's positive. It's 2 away from the nearest inert gas, helium. All right, perchlorate, I know this does not end in IDE, so I know it's a polyatomic ion. So I look at a polyatomic ion list, I see the charge is -1. All right, so we can write the formula down here, the elements, or the ion symbols, Be for beryllium, and I look on my polyatomic ion list and I see perchlorate is ClO4. Right, now we're just going to take these charges and flip them to give us the how many's. Right, so when I do that, the 1 is going to come here. Notice, we don't care about the sign. We're just looking at the magnitude of the charge, not the sign. Right, so I mean, we can't have -1 beryllium atom or beryllium ion. So this 1 is going to come here. We don't write the 1. The 2 is going to come here. But again, that looks silly. So I know I need parentheses. I know I need parentheses. Again, if you have more than 1 copy of a polyatomic ion, you must enclose it in parentheses. Must. All right, now, so that's beryllium perchlorate. You still got to deal with the waters here. All right. Hexahydrate. So hexa is 6. So I'm going to put a bullet. All right, so a bullet separates the non-hydrated part of the compound from the hydrated part. So hexa is 6, and hydrate is water. Hydrate is water. Okay? Hydrate is water. All right, any question there? Any question? And again, we can always check and make sure that this is neutral because beryllium is +2 and each perchlorate is -1. They add up to neutral. Remember, all compounds have a neutral charge. All compounds have a neutral charge. Okay? So again, this is the same as what we did last class, except we're just adding the waters of hydration. We're just adding the waters of hydration. Okay? Let's do one more here. Let's do one more. So this is one that quite often people will leave out. Let's start with the name this time. Now we'll start with the formula. I want to illustrate a point here on with this one. Okay, so just name of cation, calcium. I cover up the calcium, what's left is my anion. What's left is my anion. I see two elements, I know polyatomic ion. I see parentheses, reinforcement that this is a polyatomic anion. So I look on polyatomic ion list, PO4 is phosphate. Phosphate. Okay, now I have my waters of hydration, right? There's only one. There's no number written there, so I know there's one. I look at that prefix list, and mono is one. And yes, we do write a prefix if there's one. We don't write the number one, but we do write the prefix for one, right? So monohydrate, monohydrate, right? Monohydrate. Okay? Any questions there?
I haven't watched the last video from this class, but what's a polyatomic ion briefly?
Say again?
I haven't watched the last class video, so I'm just wondering what a polyatomic ion is real quick.
What it is?
Yeah.
Remember, the definition of an ion is an atom or a group of atoms. An atom or a group of atoms that has an electrical charge.
Correct.
Okay? So, polyatomic anion, and I think I did email this list to everybody last class. All right, so you do have the polyatomic ion list.
Yeah.
So a polyatomic anion would be a negatively charged atom or group of atoms. A negatively charged atom or group of atoms. So the polyatomics are the group of atoms, or the group of atoms. Okay? If you remember 2 classes ago, now the anions we dealt with were like N3 minus, right? Nitride, or oxide, or fluoride, right? So these are monoatomic or monatomic anions, right? But they can also have more than one atom in them, more than one atom also, right? So that's that list. Okay. Is that Miss Lolly?
Yeah.
Okay. Yeah, sorry about not posting that. All right. But you have it now. Okay. So now we have the name. Let's do the flip, the reverse of it, and come up with the formula unit on top. And no cheating. We have it up there, so we know what our answer should be. So here I'm going to write calcium is +2. It's a metal, so positive, and it's 2 away from the nearest inner gas, argon. Phosphate, it does not end in IDE, so I know it's a polyatomic, right? And that's 3 minus, right? So we're going to write the symbols down here. Calcium is Ca, phosphate is PO4, all right? And we're just going to take those charges now and flip them. The 3 is going to come on the calcium. The 2 is going to go with the phosphate, all right? But that's multiple copies of a polyatomic anion, so I need parentheses. I need the parentheses, okay? So now we deal with the waters. Now we deal with the waters. So I'm going to put a bullet. I know mono is 1. We don't write the 1. Hydrate is water. H2O. H2O. Okay? Any question on that one? Actually, I'm going to do one more. I was going to stop there, but I think we'll do one more. Hey, does anybody have a question or comment here?
I noticed you
Oh,
phosphate. I noticed in this one you used phosphate, and in the previous one you used phosphite. Is that because it's a polyatomic compound?
No, they're 2 different polyatomic ions. If you look at your polyatomic ion list, you'll see there's PO4 and PO3.
Okay.
You'll see there's SO4 and SO3. You'll see there's NO3 and NO2. Okay, they're just 2 different polyatomic ions, that's all. Just 2 different polyatomic ions. I'm not sure I satisfactorily explained what you were asking there. Did that help at all? Hello?
Yeah, a little.
Okay, I mean, it's just two different ions, that's all. I mean, it's just like oxide and sulfide are two different monoatomic anions, right? Just two different polyatomic anions. Okay? All right, I'm gonna do one more here.
Hey, Raymond,
Yeah,
for the waters of hydration, how come when we write the formula down, we have to use a bullet point?
it's just by convention. That separates the non-hydrated part from the waters of hydration. It's just convention. I
Okay.
don't know who started that convention, but I mean, everybody does it. Everybody does it.
All right, sounds good. Thank you.
Now let's do one. And again, these probably aren't real compounds, but that's okay. I have a big database, like 120 pages with a bunch of ionic compounds, but for our purposes here, it's okay. All the ones on your assignment are real compounds, by the way. So let's look at this one. Let's look at this one. Okay. You got to be careful when you have peroxide. You got to be very careful. Okay, we'll give you a chance to write that down. So we're going to come up with the formula first, the formula unit. Lowest whole number ratio between the cations and anions in an ionic compound. Okay, so I look at periodic table. Strontium atomic number 38 has a charge of +2. And remember, we write the number first and then the sign. That lets us know that it's a charge. Now, here I have an anion that ends in IDE. Now, you might be tempted to look on the periodic table, but there's no element that has a name resembling that. There is oxygen, but this is peroxide. So I'm going to look on my polyatomic ion list. And remember, there's 3 of them. The first 3 polyatomic anions on that list that end in IDE: peroxide, cyanide, and what's the other one? Peroxide, cyanide, and hydroxide. So I see that the charge on peroxide is -2. -2. Okay, so I'm going to write down the symbol for strontium. I'm going to write down the symbol for peroxide. Remember, that's not 2 oxides, that's 1 peroxide. Right, now I'm going to take these charges and flip them. Take the charges and flip them. So it gives me 2 strontiums and 2 peroxides. But again, I'm going to need parentheses there. Otherwise, it looks like 22 oxygens.
Why
Okay?
do we put the charges?
Sorry?
Why do we put the charges?
Because that's going to tell us how many of each ion we need.
Oh, I see.
Right? It's telling us how many of each ion we need. Yeah, it's a good question. Now, we see we have a common factor here of 2. So we're going to divide out by 2 to get rid of that common factor. And when we do that, right, we end up with just 1 strontium and 1 peroxide. Right, 1 strontium and 1 peroxide. Now let's check and make sure that that is in fact neutral. Strontium's charge is +2, peroxide's charge is -2. Right? Now, suppose you were given, actually, we'll save this for the end. Let's finish naming this. Right? Now we have the waters of hydration. So octa is 8. Right? Octopus has 8 legs. All right, and hydrate, H2O. So there we are. There's the formula. There's the formula. Okay. Now to name this, just name of cation, name of anion. Strontium, the metal is strontium. Right, and the anion is peroxide. And then 8 is octahydrate. Right, octahydrate. Okay,
All right.
any question or comment?
Nope.
I have a question.
Mhm.
All right, does everybody have this written? I can erase it.
I have it written.
Let's take a look at just that. How do you know whether that's peroxide or oxide? How can you tell?
It's not negatively charged.
Yeah, here's my metal cation, that's positive, so this has to be negative. That's my anion. And besides, both peroxide and oxide both have the same charge, -2. But just by looking at that, how can you tell whether it's peroxide or whether one peroxide or two oxides? How can you tell? Remember that, let's get them up here. O2 minus is oxide. O2 minus 2 is peroxide. So how can I tell whether that's two oxides or one peroxide? How can you tell?
Because strontium doesn't have a 2 with it.
Say again?
Because strontium doesn't have like the 2 with it. Like it's neutral. It's fully simplified.
Who's saying that?
Lucas?
Lucas. Lucas, I'm sure you're on the right track.
Am I just saying it wrong?
You're not saying it very clear. I mean, I think I understand it because I'm the teacher, but I'm not sure you could convince anybody else in the class of what you're saying. You're not being very specific or detailed.
So strontium does not have the subscript 2.
Well, so what? What does that mean?
So if it was 2 oxides, then the strontium would have to have the +4 charge to make it neutral.
Yes, very good. Very good. Let's take a look. Strontium's charge is +2, right? Strontium's charge is +2. Now, if this were 2 oxides, 2 of these, right? Well, each one of them is -2, right? If that's 2 oxides. Each oxide is -2. This is not neutral, right? I have 2 positives and 4 negatives. That does not add up to 0, right? So it cannot be strontium oxide. But if I do this and say, okay, that's 1 strontium, and this is 1 peroxide. 1 peroxide is O2 with a charge of -2. Now it's neutral. Now it is neutral. Okay? Again, you have to be very careful with peroxide. Let me give you another example. This might even be on the assignment. We can write this. This is sodium oxide. All right, each sodium is +1 and the oxide is -2. That's neutral. That's neutral. But let's look at this compound. All right, Na2O2. Now, each sodium is +1. If I say this is 2 oxides, then that's -2 and -2, not neutral. So that cannot be sodium oxide. It must be sodium peroxide. That's just 1 oxide, right? You can always tell whether it's oxide or peroxide by writing the charges out and figuring out which one gives a neutral compound. Remember, all compounds must have a neutral charge. We talked about that last time. All compounds must have a neutral charge, right? So that's one way to do it, or the only way to tell whether it's oxide or peroxide. Write the charges out and figure out which one gives you a neutral compound. Okay? Any question there? Any questions? All right, let's move on So, so now I gave you the 4 pages of representative ion nomenclature last class, and I asked you to do 5 of any 10 on top. So now that you know how to do the waters of hydration, I'm going to ask you to do the 5 on the bottom, right? The 5 waters of hydration on the bottom. Okay? So you should be doing 10 on each page. 5 of any 10 on top, and then the last 5 on each page. The last 5 on each page. And remember, on that assignment, we went over it last class. The first 2 pages, you have monoatomic anions. The last 2 pages, you have polyatomic anions. Right? So it tells you right on the assignment which type of ion you're dealing with. Okay. So do we have any questions here with this? Any questions?
No.
Okay. So let's move on to naming molecular compounds. All right. Now, let's draw that little flow chart one more time. All right. We drew this last class, but won't hurt to see it again. So 2 main types of compounds, ionic and molecular. Ionic and molecular, right? And we said compounds have chemical formulas. And ionic compounds have formula units. Right, so the chemical formula for an ionic compound is called a formula unit. Right, the chemical formula for a molecular compound is called a molecular formula. Molecular. Okay, now we gave a rigorous definition for a formula unit last class, smallest whole number ratio between the cations and the anions in an ionic compound. So let's give a rigorous definition for molecular formula, because it's actually quite different from the definition for a formula unit. It's actually quite different, as we're going to see in a moment. Okay, so what's a rigorous definition for a molecular formula? Well, I'm not sure this is the textbook definition, but it'll work for us. Right, a molecular formula. Okay, a molecular formula indicates the actual number of atoms of each element in one molecule of a molecular compound. Okay, a molecular formula indicates the actual number of atoms of each element in one molecule of a molecular compound. Okay, I'll say it again. The molecular formula represents the actual number of atoms of each element in one molecule of a molecular compound. Indicates the actual number of atoms of each element in one molecule of a molecular compound. Okay. Now, do I need to say that one more time?
Please.
Please? Okay, molecular formula indicates the actual number of atoms of each element in one molecule of a molecular compound. Okay, indicates the actual number of atoms of each element in one molecule of a molecular compound. So we can take a look. Something like this is perfectly valid in a molecular formula, right? We can write glucose. Notice there's common factors there. That's perfectly legitimate in a molecular formula. Perfectly legitimate. Yet, it's not okay in a formula unit. This is not okay. Because there's a common factor there. You have to divide out by it. So NF is correct. Na2, F2 is not correct. There's a common factor there. Okay? Again, common factors are perfectly valid in molecular formulas, not valid in formula units. Not valid whatsoever in formula units. Okay? Once I erase this, we'll talk about the lowest whole number ratio here in a moment. Okay, but does everybody understand this? So if I take a look at this compound, okay, indicates the actual number of atoms, 6 carbons, 12 hydrogens, 6 oxygens, of each element, okay, of each element, in just one molecule. So if I'm holding one molecule of glucose in my hand, that molecule has 6 carbons, 12 hydrogens, 6 oxygens. Okay? Again, and why is it okay to have a common factor here? Because it's not a ratio. It's not a ratio, all right, like it is over here. Okay, in a formula unit, it's the ratio between the number of cations compared to the number of anions. You want the smallest whole number ratio. Okay, whereas that's not the case here. Okay, let's see here. I'm going to erase this. So this is worth mentioning here. Let's go back to C2H2. So that's a molecular formula. Okay, but I see there's a common factor there, so I could write this as CH. No such compound as this, but it has a different name. This is what's called a molecular formula. Molecular formula. And this on the bottom is what's called, I'm not going to give you any problems with this, but this is what's called an empirical formula. An empirical formula. Right? So formula units are empirical formulas. Okay? Molecular formulas do not have to be empirical. And what is an empirical formula? The smallest whole number ratio between the atoms of the given elements in a chemical compound. Okay? Let's look at the glucose one. Let's look at the glucose one. So we have C6H12O6. All right, so that's the molecular formula in black. What would the empirical formula be? Well, there's a common factor of 6 there, right? A common factor of 6. So 1 carbon, 2 hydrogens, 12 divided by 6 is 2, and 1 oxygen. So here's the empirical formula for glucose. Here's the molecular formula for glucose. Actually, there's many, many sugars that have this molecular formula. Many, many sugars. Glucose, fructose, and then there's alpha D glucose, beta D glucose, alpha L glucose, alpha D or beta L glucose. So at least 4, and then you have the fructoses. All have the same chemical formula. This is another difference between ionic compounds and molecular compounds. For an ionic compound, there's a formula unit. There's no ambiguity. That stands for one compound. Okay, there's no ambiguity. Once you have a formula unit, you know what the compound is. But you can have, but many molecular compounds can have the exact same molecular formula. Right? So you can have more than one molecular compound with the exact same molecular formula. Exact same molecular formula. Okay? So the molecular formulas are not necessarily unique to a given compound, whereas formula units are. Formula units are. Okay, but let's see how to name these beasts. All right? Let's see how to name these beasts. That's what we're after. So again, like glucose and fructose have the exact same molecular formula. C6H12O6, but they're quite different compounds. All right, now, I'm going to take over the screen here for a moment, And I will give you this. I will print this out or email it to you. I wanted to do it earlier, but okay. So we take a look here. Okay, first we see all chemical compounds have a neutral charge. You already knew that. We already learned that last week. Okay, molecular compounds do not contain a metal cation. All right, so this is one way of looking at a chemical formula and right away, right, telling whether it's an ionic compound or molecular. All right, most ionic compounds begin with a metal because we always put the cation first. Right, we always put the cation first. So cations are metals. Right, although we did have the one exception, or we had the one polyatomic cation, NH4 plus, ammonium cation, NH4 plus. But other than that, all the ionic compounds that we will see will begin with a metal. If it doesn't begin with a metal, you know it's a molecular compound. You know it's a molecular compound, with that NH4 plus being the one exception. Okay, being the one exception. So how are we going to name these? Now, we're only going to be concerned with very, very simple molecular compounds. Okay, what are called binary molecular compounds. They're only going to contain two different elements. They're only going to contain two different elements. Okay, so the first rule here, the names of the elements are written in the order in which they appear. Right? The names of the elements in the order in which they appear. Right? And then rule number 2, we use a Greek prefix. We already know what the Greek prefixes are, right? To indicate the number of atoms of each element. The number of atoms of each element. And then rule 3, the last element ends in IDE. The last element ends in IDE. That does not mean it's an anion. All the atoms in a molecular compound we can think of as being neutral. We can think of as being neutral. Right? So just because I'm getting a signal that I'm losing my internet here, right? Just because that last element ends in IDE does not make it an anion, right? So then we have this rule A and B. This rule A and B. When there's only one atom of the first atom type, then we get rid of the prefix mono, all right? And the final vowel in a prefix is often dropped when an atom type also begins with a vowel. If you want, you can completely ignore rule B and I will not mark you wrong. I will not mark you wrong. Okay? Let's see, I think I'm going to stop sharing here for a minute. And I think I have I'm going to ship you this little file right now. Right, so that way you'll have it to look at. So this is going to eat up a minute or two of this video, but that's okay. All right, so attachment. I made it for only Jasmine. I thought, gee, oh, okay, there we go. Oh, all right, now it's for everybody. All right, so the subject is just going to be lecture notes here. So if you have your email open, okay, now the attachment, lecture notes, open. All right, so it's been sent. Okay, so back to Zoom. Okay, so let's take a look. Now, let's look at, for example, We only got 10 minutes. Let's look at water, for example. H2O. All right, now we all know that that's water. But let's come up with a name for it using the rules that we just went over. All right, so we write down the names of the elements. Hydrogen. And I'm going to leave room for a prefix here, oxygen. All right? So that's rule number 1. Rule number 2 says, put a prefix indicating how many atoms of each element. Indicating how many atoms of each element. So di is 2, mono is 1 for the oxygen. All right? Then the last element must end in IDE. All right? So I'm going to write dihydrogen, monoxide. Last element ends in IDE. Right? So there's our 3 rules. There's our 3 rules. Again, you write the names of the elements in the order in which they appear. You put one of these prefixes in telling you how many atoms of each element. Right? We're only going to have 2 elements in our problems. All right? And then the last element ends in IDE. Now, you know that right off the bat. If you want to write hydrogen and oxide right from the beginning, by all means do so. All right? But I'm trying to make it systematic. Okay? Now, let's look at that rule A. Rule A says, if the first element only has 1 atom, get rid of the prefix, mono. That's not the case here. The first element has 2 atoms. That's not the case here. Okay? And then rule B does apply if you wanted to. Okay? If an element begins with a vowel, you can drop the last vowel off of the prefix. So if we wanted to change this to dihydrogen monoxide, which is probably how most people would say it. What? Okay? I will accept either of these 2. Either of these 2 I will accept. Okay? Again, if you want to never apply that rule B, I don't have a problem. I don't have a problem. You'll see in a moment what I'm getting at. Okay? So this would be the systematic name for water. Okay? Let's look at now. What if I give you the formula, or sorry, the name, and you have to come up with the molecular formula? Well, let's see. Hydrogen is H, oxygen is O, di is 2, and mono is 1. H2O. Very simple. Very simple. This is much easier than doing the ionic compounds. Much, much easier. Now, let's look at another one. What's the deadly gas that you breathe out every breath you take? What's that gas?
Carbon dioxide.
Carbon dioxide. So let's look at that one. All right. So CO2. All right. So I'm going to write down the names of the elements: carbon and oxygen. That's rule number 1. Rule number 1. Rule number 2 says put a prefix in for each element, indicating how many atoms of that element. So monocarbon dioxygen. Rule 3 says the last element ends in IDE. So monocarbon dioxide. So there's rules 1, 2, and 3. Rules 1, 2, and 3 apply to every one of these compounds. Every one of these binary molecular compounds. Right? 2 different elements. All right? Now, let's look at rules A and B and see if we can apply them. Rules A and B you apply as needed. And rule A says if you only have 1 atom of the first element, drop the prefix mono. Drop the prefix mono. All right? So now we're down to carbon dioxide. Carbon dioxide. All right? Carbon dioxide. All right? Now, Now you have to apply that rule A in this problem. Now let's look at rule B. Rule B says if you have an element that begins with a vowel, oxygen begins with a vowel, you may drop the last prefix off of the last vowel from the prefix. So that would be, I'm going to write it in a different color. Let's write it in red. So if I was to drop that I off of the di, this would be carbon dioxide. Carbon dioxide, which sounds kind of silly, right? That sounds kind of silly. Okay? I'll give you a hint, and actually I just realized this after all these years of teaching this. I guess rule B really should only apply if the prefix has more than one syllable. If the prefix has more than one syllable, then you should drop the last vowel off of the prefix. The prefix just has one syllable, keep the vowel. Keep the vowel. All right, you'll see, we'll do one here in a moment. You'll see what I mean. Okay? Any question there? Any question? And again, I've given you the name. How do we come up with the formula? How do we come up with the formula? All right, well, carbon is C, oxygen is O. There's no prefix here, so I know it's 1. Here, 2. Carbon dioxide. Carbon dioxide. Very, very simple. Very, very simple. Okay? We got time for one more. One more. Any question on this one? Any question? All right, let's look at one more then. Actually, I don't have my database up on the computer here, so I'm just going to make one up off the top of my head. I'm not sure this is real. Oh, yeah, here we go. All right, so P2O5. All right, so we're going to write down the names of the elements, phosphorus and oxygen. Phosphorus and oxygen. Now we're going to put the prefixes in. Di is 2 for phosphorus, and penta is 5 for the oxygen. Penta. Okay? Now, that's rules 1 and 2. Rule 3 says the last element must end in IDE. So the pentaoxygen is going to become pentaoxide. So diphosphorus, pentaoxide. All right, that's rules 1, 2, and 3, which you must apply to every problem. Rules 1, 2, and 3, every problem. Now, rule A says if you only have one atom of the first element, that does not apply here. And remember, it's only the first element, not the second. Not the second. You should have those rules right next to you when you do the problems. Okay? Now, how about rule B? If you have an element that begins with a vowel, right there, oxide, you may drop the last vowel off of the prefix. Okay, so we can do that here. We can call this diphosphorus pentoxide. Pentoxide. Either one is acceptable. Either one. I'll take this one. I'll take this one. Okay, and again, if you want to completely forget about rule B, that's fine. What's the deadly gas that comes out of your car exhaust? Well, there's many, but
Isn't it carbon monoxide?
carbon monoxide, right? So that's carbon monoxide, since we're out of time, right? So if you wanted to, if you drop that rule B, this would be monooxide. You'd have 2 O's back to back here. 2 O's. And I will not mark it wrong. Either one is fine. Either one is fine. Okay? Any questions or comments? Do you think you could do an assignment on this? Of course, you can just Google them. Actually, let me just do one here real quick. Any question or comment before I erase this one?
No.
Okay. Since a lot of us, since it snowed here in Los Alamos last night, we're going to be turning on our propane stoves here pretty soon. So propane is P3H8. C3, not C. I'm thinking P for propane. C3H8. All right, so what would this be called? Well, 3 carbons is tricarbon. And 8 hydrogens is octahydride. So there's another name for propane. Of course, no one would ever call it this. We would just say propane. Okay? We would just say propane. Right? But this systematic approach that we learned today would be a perfectly valid name for propane. Okay, I think I'm going to stop recording here since there's no questions, and then we can talk a little bit about a few things.